Let me begin by thanking Partha and the Academy for inviting me. It's a great honor to speak on occasions like this when we are celebrating the greatest living statistician on earth, his 100th birthday. See, I was not a student of RAO, though my title sort of gives you misleading information probably. And I remember the first time I saw RAO when I was a student in my second year BStat. Professor Rao came and he was giving a lecture in 3.0, that third floor. That used to be the largest room available in our institute at that time. So we were sitting in the probably nearly the back rows, and in the front rows we had all our star teachers sitting there, like Professor J.K. Ghosh, Jagobrat Roy, Ashok Mitra sitting there. And it was quite an experience because when these teachers were teaching us, we would just stare at them with great respect and fear. And these people are now looking at RAO with a similar thing. And RAO was really teaching them as if they were just his students, you know. It's like he will say a few things and then he says, do you know how to solve this problem? Or he will ask Jagobrat Roy, do you have a program to compute this? Okay. So that was my first exposure to RAO. Okay. Then there are several times I have seen him as a student, but my first interaction with Professor Rao was quite surprising and very interesting. And for any young statistician or for any young scientist, that's a great honor, I would say, the way that interaction took place. When I was elected a fellow of this academy, I got a congratulatory note from him. He was the first person to congratulate me. And later on, I found out that's his habit. Whenever he sees any statistician or young mathematician getting elected to any of these fellows of the academy, he will take the personal initiative to congratulate them, to write an email. So I was almost stunned to receive that email from Dr. Rao. Okay? And it has happened when I was elected fellow of INSA also. Okay? So he congratulated me. Okay? So later on, I have met him several times and we had many interactions, but I still remember that day when I received that congratulatory mail from Rao when I was elected a fellow of this academy. Okay. Now, the title of my talk is Learning Mahalanobis Distance from Rao. 2 years ago, we were celebrating 125th birth anniversary of Prashant Chandra Mahalanobis. And few months back, I gave a talk in this academy in the mid-year meeting on Prashant Chandra Mahalanobis. Now we are celebrating 100th birth anniversary of Rao. And so I thought I will be talking about something which connects these two stalwarts in statistics in some way. Okay. Now, let me begin with a question for the students. Rao. Now, the middle part, Rao, is Radhakrishnan. You know that, right? So I see you are nodding. Do you know why he was named Radhakrishna? Anybody has any guess? So Rao has an autobiographical essay that appeared in this famous book, Glimpses of India's Statistical Heritage. If you are interested in the history of development of statistics, it's something worth reading. And most of these essays are written by the stalwarts who developed statistics or contributed to the development of statistics in this country. And there Rao says something. So what will be your guess? Why Radhakrishna as the middle name? There are people from the south here, I guess.
One tradition is that grandfather's name.
Okay, that's not the right guess.
I know.
Okay.
But we have a practice in South India.
Okay. So he says, according to him, he was the 8th child, like Krishna. Okay. So that's why Radhakrishna.
I was also the 8th and named Krishna.
Okay. So that's also a custom probably in the, okay. So please ask questions whenever you have difficulty understanding what I am saying, okay? Because if you don't ask questions, it becomes a monologue and it's very boring, okay? So you should feel free to interrupt me anytime you have difficulty understanding something. There may be a few technical things I may not be able to explain in full details, but it doesn't matter. Ask your questions and I will try my best to explain things to you. Okay. So let me begin by telling you what is Mahalanobis distance and how it started. Okay. So Mahalanobis met Nelson Annandale in the 1920 Nagpur session of the Indian Science Congress, and Annandale asked Mahalanobis to analyze anthropometric measurements of Anglo-Indians in Calcutta, and that led to the discovery or invention of this famous Mahalanobis distance.
Sir, please explain Anglo-Indians to our students. This generation may not know, really.
Okay.
Really?
Okay, so you know India was under British rule for a long time, and people were coming here from England to work here and to do business here, and some of them settled here. Okay, and there is a large community of, even now in large community of those English people living in several parts of Bengal and other places. Okay, they are called Anglo-Indians. Okay, now who was Nelson Annandale? Nelson Annandale was a civil servant. He was the Director General of the Geological Survey of India at that time, and also the Director of the Indian Museum in Calcutta. Okay, so he was an anthropologist, and he was interested in the anthropological data related to Anglo-Indians. Okay, clear? Okay. So he was comparing different groups, and that's how Mahalanobis invented this. That led to the invention of Mahalanobis distance. And you see, his first paper actually appeared in the records of Indian Museum, and actually this is the one that has all the details on all the statistical and mathematical details, and that appeared in Journal of Asiatic Society. And why it's in the Journal of Asiatic Society, that's another story. That's not something that I will talk about today. Okay. Now, what is Mahalanobis distance? I have to give you the expression. Okay, so this is the Mahalanobis distance. I presume all of you are familiar with basic matrix algebra. Okay, so I think the technicalities are not going to go beyond this.
They may not be aware as to why you measure distance. Maybe you should explain that.
Okay, okay. So suppose you have two groups of people, like the Tamilians and the Bengalis. Okay, and I want to compare these two groups, like how different they are. So I have anthropometric measurements on them, like their heights, various measurements. Usually these anthropometricians take a lot of measurements on their skulls, okay, various other measurements, and then they get a set of variables like height, and then various measurements on the skull, length of hand, and all these things. And then this mu1 is like the mean for one group, and then mu2 is the mean for the other group. And sigma is the dispersion. Okay, and here we are assuming that they have a common dispersion. So the distance between the two populations, that is defined like this. You see, this is like a row vector, and this is like a column vector. So when I write a transpose, that means it's a row, and when I don't write a transpose, that means it's a column vector, and this is sigma inverse. So it's a quadratic expression or quadratic form. So at the end, it's a real number. And because sigma, you know, if you are familiar with dispersion matrix, you know it's a positive definite matrix. So this is going to be a positive number. Okay, so that's the distance. So if the means are very different, then the distance will be large and the populations will be very different. And if the means are close, you say statistically they are very close. That was the motivation. Okay, the difficulty is this sigma inverse. Okay, because Mahalanobis wanted to look at difference in means in relation to their spread or dispersion. So sigma inverse sort of standardizes the things before you calculate the distance, and that's why that sigma inverse appears there. Okay, it's really the square of the distance. The square root should be the distance, but I am writing it like this. So because Mahalanobis, we usually call it Mahalanobis as d square, so it is d square. D is the distance. Okay.
Sir, this is the mu1 and mu2 mean. Okay, suppose some constant p variate to random vectors, right?
Yeah, so they are p variate. So mu1, mu2 are p dimensional.
P-dimensional. Suppose that one random vector is here and someone is there, some vector. Then the distance between like this distance is Mahalanobis distance, or I mean the distance means what is defined by.
Okay, let's say that sigma inverse is not there. Suppose sigma inverse is the identity matrix. Then what will be this expression? It is just the Euclidean distance between mu1 and mu2. Okay, so you understand why that is the distance. Now, being a statistician, Mahalanobis was not interested in looking at the straightforward Euclidean distance, because Mahalanobis thought, which is quite logical, that distance between means should not taken just as such, it should be standardized by the spread, and that is why this sigma inverse is coming up. So the distance may be big or large, but you need to decide that based on the spread in the variable. Okay?
Dispersion plays a role.
Yes, dispersion plays a role here. So if that sigma inverse is not there, it's just the standard Euclidean distance that you have learned in your analytic geometry. Okay? So it is that placement of sigma inverse that makes it Mahalanobis distance. Rather d square, as he said, it is the square of the distance. Okay?
It's free from units.
Huh?
Free from units.
It will also be free from the unit of measurement because of the standardization. Very good point, right? So usually there are, I mean, this you see this articles, they are in some obscure places. It's not easy to get access to these papers anymore. So most of the time, that paper that we refer to, which is available in the net, is this one, which is, it appeared in the Proceedings of the National Institute of Science, which is the predecessor of Indian National Science Academy, which was in Calcutta at that time. So this is the 1936, Mahalanobis gave a special lecture on d square, or Mahalanobis distance, and the title of the article was on the generalized distance in statistics. Okay, so
Make one comment for the students, if they want to read it. The first paper will be now published in Shankar series B.
okay, all right,
Series B,
okay,
and it's already online.
okay.
People can read that.
That 1922 paper, you mean? Okay, so that is in the records of Indian Museum.
No,
No, Asiatic Society.
That Asiatic Society paper, okay, yeah, that's very good, okay, so that's very good. It's not easy to access that, okay. Yeah, that's the paper that has all the statistical and mathematical details that Mahalanobis worked out, okay. And the subsequent mathematical developments are due to S.N. Roy and R.C. Bose and those people, okay. Good, okay. So I will show you just one page of that paper. That will be a good experience for you, okay. So see, we write mu's and such things. This is just one page of that paper, okay. So you see, Mahalanobis is writing something delta square, and see, in those days they didn't use sigma. So this S is summation. So summation I from 1 to p, okay. Now let's ignore these things. You come here, okay. You see here, so he writes alpha for the dispersion matrix, okay. He doesn't write sigma. And then you see he writes alpha ij, which is an entry related to the inverse or from the inverse of the matrix, and then he writes this expression cofactor divided by determinant, and you understand why, right? Why this cofactor and determinants are coming up? Look at this expression. There is a sigma inverse, and the first formula or first expression that we have learned for inverse, what is that? Say it. A adjoint, so the cofactors will come. So that is why this cofactor and such things are coming up. Now imagine usually these anthropometricians have something like 100 measurements on an individual. So it will be 100 by 100 matrix. So how will you calculate the adjoint of a 100 by 100 matrix? How many cofactors you have to calculate? It will be almost an impossible task, right? And this poor C.R. Rao, when he was employed as an apprentice in Indian Statistical Institute in early 40s, he was given a primitive computing machine, and he was asked to analyze data, not to the Anglo-Indian population, that was earlier. So it's from the United Province, it was from UP. At that time, there were some anthropologists who were working on anthropometric measurements coming from the various tribes living in United Province at that time. Now it is Uttar Pradesh. Okay, so
That was an adding machine.
Huh?
That was an adding machine, right?
Yes, it's essentially an adding machine they had. Yeah. So this poor C.R. Rao had to do all these computations for his professor. So I think somebody has already said this. In the institute, there is one professor, Professor Mahalanobis, and there is Dr. Rao. Okay. Now Dr. Rao was not doctor at that time. It was in early 40s. Okay. Dr. Rao became doctor in 1948. So this poor C.R. Rao was doing all these computations. So he realized that he is not going to survive if he has to compute all these cofactors and such things. Okay. So a lot of people don't know this. That led to a beautiful result that he invented while working on this problem, and that is given actually in his famous book, Linear Statistical Inference. It doesn't give it as a result invented by him, but it is the only textbook that gives the details of such a result. So what you do there, I will not tell you the details of that result, okay? I will tell you the main idea. So what you do is that you use a very interesting formula for the determinant of a partition matrix. When you partition a matrix, there is a nice formula connecting the determinant of the whole matrix with the determinants of different partitions. And he used that very cleverly to come up with a very intelligent way of computing Mahalanobis distance. Essentially what you do is that, suppose you have p variables, that gives you a p by p dispersion matrix, and you add an extra column and an extra row there, which is just the difference of the two means, and then put a 0 there to make it a p plus 1 by p plus 1 matrix. And then you do a sweep out operation on this matrix to make it an upper triangular or a lower triangular matrix, whatever you like. And then the last entry that you are left there, the rightmost lower entry with a negative sign, that will be Mahalanobis distance. So forget about computation of all these cofactors, adjoints, it comes so nicely. So that was one of his first invention actually, to compute Mahalanobis distance in a way that is feasible with these primitive machines. Okay. So a lot of people don't know this. We were told this by some of our teachers. I am telling you this story. Sometimes it is the necessity, necessity is the mother of invention. Okay. So so he invented this. So this is one of his very early contributions towards development of the computational methodology for disk square. Okay.
We don't teach sweep-out method anymore.
So yeah, we probably don't teach that. But Mahalanobis distance, if you compute that using any statistical software, it is actually computed using that algorithm. You cannot compute it using adjoint matrix, then you will be dead. Okay.
Gopal, I have a question.
Yeah.
This sigma is unknown, isn't it? So
No, it is estimated from the data.
that's what I'm saying. I wanted you to
So it is estimated. So all these parameters are estimated from the data. So you take the mean of the data, you take the dispersion of the data, and that's what you use for.
Sample variance covariance.
Yes, it's a sample variance covariance matrix, right? Okay. Now, what is subsequent connection of C.R. Rao with that? Now, C.R. Rao, when he joined Indian Statistical Institute, shortly after that, in 1941 in Calcutta University, they started the master's program in statistics, and C.R. Rao joined that along with 5 other students. Horikinkar Nandi was his classmate at that time. And so these people were learning statistics from more senior people who were doing part-time teaching in Calcutta University. And Prashanta Chandra Mahalanobis was the honorary head of that department in Calcutta University. And I will tell you, so if you are afraid of asking questions, this is something you should learn from C.R. Rao. This is from C.R. Rao's own writing. I will read 2-3 sentences from his writing. Okay, here. So this is what C.R. Rao writes about his experience as a master student in the first statistics program in India in Calcutta University. None of the teachers had any experience in teaching statistics, and further they were as ignorant as the students in some areas of statistics. As there was no textbooks on statistics, the teachers had to learn by reading original papers and then teach. The courses given in the first 2 years benefited the faculty as well as the students. And such a program led to development, or it produced people like Horikinkar Nandi and C.R. Rao. Okay? And these people all learned by asking questions among themselves. So learn to ask questions. Don't keep silent. Then you don't learn. Okay? Okay. So this is beginning of his training in statistics. And then after 1943, when he graduated, he joined the Indian Statistical Institute as a technical apprentice. Okay? And then I think, so he was working on this data that I have already mentioned. And then something interesting happened. I will come to that. So this is the, so when he was teaching when he was working as an apprentice, he was also doing some teaching. And you have heard from some of the earlier speakers that while teaching, he invented two of those great results, Rao-Blackwell theorem and Kramer-Rao lower bound. C.R. Rao has a lot of interesting anecdotes to tell. If you particularly read this essay, you will learn that. One of the anecdotes that he writes here, and this is something he had told me also, okay, when once I was talking to him when he was visiting India in Hyderabad. So this Kramer-Rao inequality, okay. So his name was C.R. Rao. So once he was traveling in Iran and his luggage got lost. And then he complained about it and then he went to the hotel. After some time he gets a call from the airline and the lady from the airline tells, Professor Kramer-Rao. Then he says, no, I am not Kramer-Rao, I am C.R. Rao. No, there is a person here who is looking for you. He says you are Kramer-Rao. Okay. So this is one of the anecdotes. Okay. So C.R. Rao became Kramer-Rao in Iran. Okay. So anyway, so he invented Kramer-Rao lower bound and Rao-Blackwell theorem when he was teaching, and he didn't have a PhD degree at that time. So now coming to his PhD. Okay. So how did he end up doing his PhD work with Fisher? So this is the story. I'll read again from his own writing. In 1946, the professor received an unusual cable from J.C. Trevor, a Cambridge University anthropologist. The cable says, kindly depute a scholar from the Indian Statistical Institute to the Cambridge University to apply Mahalanobis distance analysis on some anthropometric data collected by the University Museum. If you are watching the movie that was shown, C.R. Rao mentioned that there. Okay? And the two people whom Mahalanobis sent for that, one of them was C.R. Rao, and the other person, probably many of you don't know the name, he is a very famous anthropologist, his name is R.K. Mukherjee. So this...
They were on the film yesterday.
Yes, R.K. Mukherjee was also on the film, yeah. So these two people went there and they worked on it, and before that, Fisher visited India a few times. So C.R. Rao had a chance to meet Ronald Fisher when he was in India. So when he was in Cambridge, this is what he writes. So shortly after reaching Cambridge, I met R.A. Fisher, who was the Belfer Professor of Genetics at that time and whom I had met in India during his visit in 1944. I told him that I had enrolled myself as a research scholar and asked him whether he would agree to be my supervisor. Okay. So that was the beginning of his interaction with R.A. Fisher as his PhD supervisor. And then he writes, he agreed but suggested that it would be a good experience for me to work also in his laboratory where he was breeding mice for linkage studies. Okay. So Fisher was a geneticist. Mahalanobis was a physicist, Fisher was a geneticist, and poor C.R. Rao is getting sandwiched between these two people and becoming statistician. Okay. So so C.R. Rao was originally deputed to Cambridge to work on this anthropological data in the University Museum. And then he enrolled as a PhD student, and Fisher asked him to do these linkage studies with mice. So at one place he writes this, I kept myself busy in Cambridge dividing my time between bones and stones at the University Anthropological Museum and mice at Whittingham Lodge, the official residence of the Belfort Professor of Genetics. So he was busy with mice, bones and stones in Cambridge for 2 years. That's what he writes. Okay. So now let's come back to Fisher. So here is Fisher's paper, and remember it is the same date, 1936. It appeared in the Annals of Eugenics, the use of multiple measurements in taxonomic problems. And Fisher considered this problem of classification of different iris species. He had measurements on the lengths and the widths of the sepals and the petals of the flowers of Iris setosa, Iris virginica, and Iris versicolor. So his problem was like this. So he had measurements on these different iris varieties, and he wanted to use those measurements to distinguish or discriminate among these different iris flowers. So he converted the taxonomy problem into a statistical problem. So it's like you'll be given some measurements. It's like I'll be giving you the measurements on some individual, and you have to tell whether this person is from Punjab or from Tamil Nadu. Something like that. Okay. So that was his problem. Now let's look at Fisher's discriminant function and Mahalanobis distance. I have already told you what is Mahalanobis distance. Now here I am defining Mahalanobis distance of a particular data from the population with mean mu and dispersion sigma. See, it's a distance, or rather distance square. So just like I can define distance between two populations, suppose I have a population and I give you a data or an individual. You can try to calculate what is the distance of that individual from that population, and that is calculated like this. So it is this thing, and Fisher formed the linear discriminant function which had this formula. How he formed that I will be telling you in a few minutes, but this is Fisher's linear discriminant function. You see, it's a linear expression, right? It's linear in x, so you have the two means for the two population, and Fisher assumed that they have the common dispersion, and this is the linear discriminant function. Okay, so Fisher said you calculate the value of this linear discriminant function, and if this value is greater than 0, then it will be coming from one population, and if it is smaller than 0, it will be coming from another population. That was Fisher's idea. Now, how are these two things linked and why Fisher thought so? Let's try to understand that step by step. So here is what happens. So Fisher's linear discriminant function corresponds to the separating hyperplane that separates the points which are closer in Mahalanobis distance to one population from the points which are closer to the other population. Let me draw a picture. Okay. So suppose this is one set of data and this is another set of data. Okay. So here is a point which clearly belongs to this population, whereas here is another point which clearly belongs to this population. And here is Fisher's linear discriminant function, the separating line. So if this point is on this side, Fisher will classify it as the green population. If it is on this side, Fisher will classify it as in the blue population. And if you calculate the Mahalanobis distance of this point from the blue population, you can see from the picture that it will be closer to the blue population. And similarly, for this one, it will be closer to the green population. But that was not the original motivation of Fisher to come up with linear discriminant function. That's what we know today. So that is, there is an intrinsic connection between Mahalanobis distance and Fisher's linear discriminant function. That's this. The linear discriminant function is really the separating hyperplane that separates the 2 points where one set of points are closer to one population and the other set of points are closer to the other population, where closeness is measured using Mahalanobis distance. But this is not something Fisher realized. Okay. Now, you are familiar with basic statistics, right? So you have learned about Fisher's two-sample t-test and such things. Okay. So why do you think Fisher decided for that particular linear discriminant function? I gave you a hint. So you know about the two-sample t-test. Suppose you don't have many variables, you have only one variable. Okay? So in that case, you can calculate the t-statistic between the two populations, and you can try to see whether the two populations are very well separated or not, right? So that you can decide based on your t-statistic. If your t-statistic is very large in magnitude, then you decide that the two groups are very different, significantly different, and if your t-statistics is not so large, then you do that. Then you decide that they are not so different. Okay. Now my question is, so Fisher came up with a linear function. Now if I take a linear function of the data, the entire data then becomes just a univariate data, isn't it? Suppose I have all your measurements and I take a linear function. That linear function converts all these multivariate data points into just a real valued or univariate data. So it's like I take a linear function of your height, weight, etc. Okay. Finally, I get just one number for each individual. So after that, suppose you try to do a t-test, how will you choose your linear function? Anybody has any idea? So you can choose many linear functions, and different linear functions will give you different values for your t-statistic. Which linear function is good for you when you are trying to form a linear function that distinguishes two populations? Is my question clear to everybody? So I can form many linear functions. My question is, which linear function I should take so that I can distinguish the two populations using my T statistic that Fisher invented, Fisher's T. So larger the value of the T statistic, the better it is for you, right? Because if you have a large value of T statistic, then that gives you more separation. So Fisher was trying to get a linear function that makes the T statistic very large. And so this was Fisher's motivation. So if you read Fisher's paper, that's there in the very first paragraph of his paper. So he says this. So his choice of his linear discriminant function was motivated by the fact that this linear function maximizes Fisher's two-sample T statistic computed from linear functions of the data, and Fisher claimed that that is the best linear function. The best is according to Fisher. But when you have a classification problem, what is best? It's like it should give you a classifier so that your misclassification is small. But Fisher never tried to say anything about that in the paper. Fisher only said, take that linear function which is motivated by this, and that is the best linear classifier, and if you use that, you will get good result, and left it there. But a more important question now is that if I use that classifier, how many cases I will wrongly classify and how many cases I will correctly classify? Because it's not going to be perfect classification, because you see that picture, there are these blue points here and there are these green points on this side. So there will be misclassification. So now comes this fundamental question, is this classifier really, as Fisher thought, the best classifier? The answer was not known till C.R. Rao took up his PhD research with Fisher. So this was C.R. Rao's PhD research problem. So when he started working with Fisher, actually he was the only student who was doing multivariate analysis. All other students of Fisher were working on genetics. Okay. And later on, C.R. Rao said that among my students also, we mostly had statisticians and probabilists, but he mentions about two geneticists who worked under him. They are Ranajit Chakraborty and D.C. Rao. These two people were the only two geneticists who worked under C.R. Rao's supervision. Okay. All others were either statisticians or probabilists. Okay. So this is now C.R. Rao's 1948 paper. So this is C.R. Rao's PhD thesis. So if you have not read it, please read it. Okay. This is C.R. Rao's PhD thesis, and you see there is a remarkable similarity between the two titles. So here he writes the utilization of multiple measurements in problems of biological classification, and there the title of Fisher's paper was the use of multiple measurements in taxonomic problems. Okay. You see the connection? So when C.R. Rao worked on, I said that he was working in the anthropological museum there. So Rao considered the problem of classifying human skull recovered in archaeological excavation into Iron Age and Bronze Age. So there were these skulls coming from different ages, and he was working on that. To summarize that famous paper it's actually a discussion paper in GRSS. There are many famous statisticians who are discussing it. In fact, they are raising some question. So the interesting thing is that in that, that's the only place where I see C.R. Rao getting addressed as Mr. Rao. So throughout this discussion, everybody is addressing him as Mr. Rao, Mr. Rao, Mr. Rao, like that. Okay. So at one place, Mr. Rao was asked a very interesting question by some people that, well, so C.R. Rao proved the following optimality. Let me show you that optimality result, and then I will tell you the question. Okay. So here is C.R. Rao's result. The linear discriminant function has Bayes risk optimality for Gaussian class distributions which differ in their locations but have the same dispersion. So essentially, the result is that Fisher thought that that's the best classifier, but Fisher did not prove that that has the best misclassification rate. C.R. Rao proved that. So this Bayes optimality means that it has the best misclassification rates if the populations have Gaussian distributions. Okay. So it finally settled why Fisher's linear discriminant function is the best under certain conditions. Okay. So in fact, though it is not articulated in C.R. Rao's paper, it's actually not difficult to see from his work that this Bayes risk optimality holds for elliptically symmetric and unimodal class distributions which differ only in their locations. I mean, they don't have to be Gaussian. And so, coming back to the question, so a lot of people were asking him this question. But you have computed the linear discriminant function based on the data that you have. Whereas these optimality results are related to the distribution, the population. So how optimal it is when you are computing it from the data, and of course CRAO didn't know the answer at that time, okay, and it's a difficult question to answer, okay, it's not an easy question to answer. So some of these questions were asked during his, I mean that discussion paper in my opinion is really his PhD defense, okay, and he was fired questions from all these great statisticians and he was trying his best to respond to that, okay.
The discussion part is longer than the paper.
Yeah, discussion part is much longer than the paper, okay. And then there is a rejoinder, that's also quite long actually. And then a few anecdotes, like when he first asked Fisher for a problem, this is what Fisher apparently told him. So this is what Fisher told him when he was asking for a problem for his PhD work. Problems must be yours, I shall help if I can. So if you become a PhD student, don't complain about your supervisor. This is how you become CRAO, okay?
And then CRAO said the same thing to T. Parthasarathi.
Okay. So that's about his PhD research. And so he returned to India in 1948. He was 28 years old at that time. Now, if I go back to my first slide, you see this event also happened in 1920. So this is the year when Mahalanobis met Nelson Alden, and that was the genesis of D square, and CRAO was born in the same year. Okay, so 1920 is really this is probably the landmark year in the history of statistics. Okay. So CRAO was appointed a professor when he returned to India in 1948. Apparently, according to CRAO, when he returned, by that time in our institute we had this classification of lecturer, associate professor, professor, and Professor Mahalanobis was thinking about giving the professor positions to S.N. Roy and R.C. Bose and the associate professor position to CRAO, but S.N. Roy and R.C. Bose left shortly around that time. And so CRAO was made the professor, and at various points of time, so I want to read some of his personal comments about Prashant Chandra Mahalanobis, because that's quite a learning experience, okay. So his first impression about Professor Mahalanobis when he joined as an apprentice, okay. Okay, this is what he says. So I met different scholars and tried to interact with them. I could not meet the professor, as Professor Mahalanobis was referred to with awe and reverence by everyone. I had seen him coming in and going out of his office at odd times of the day. He had a tall and commanding figure. Everybody was alert and ready to be called in for a discussion when the professor was in. The scholars, this is the most interesting thing, the scholars maintained a diary of their minute-to-minute activities. One of the frequent entries was discussion with the professor. So that was one of the, so discussion with the professor was the most frequent entry. Okay. Nobody in the institute would tell me what the discussions were about. So this is one thing. And then the second thing that he has said about professor, so when he graduated from Calcutta University, he was given that job, and so he passed MA in statistics with the first rank, and so this is what he says. I was among the first 5 to receive the MA degree in statistics from any Indian university. The professor offered jobs to all of us in the ISI as technical apprentices on a salary of ₹75 a month. With first-class master's degree in mathematics at the Andhra University and statistics at the Calcutta University, I was expecting a higher salary. However, I accepted the job without quote-unquote asking for more and joined the ISI in December 1943. To my surprise, I found that my salary was increased to ₹150 within a month. Perhaps the professor meant it as a gift for accepting the earlier offer without asking for more. So then he goes on saying that this is a very good strategy with professor. You don't ask for more, then you get more. Okay? So then it goes on, then simultaneously there was an offer of a part-time lectureship of rupees 100. So altogether he was making something like 250 rupees, and that made him decide that he will stay in Calcutta, he will not go back to Andhra. So for 250 rupees, Indian Statistical Institute got C.R. Rao for good. So this is the history, and after coming back to India, he went on working on Mahalanobis distance. That was one of his great passion, to work on various aspects of the thing. And then something that many of us do not know, and this is we were talking in the breakfast about this paper. This paper of C.R. Rao with Varadarajan, many people don't know. As a result, many people reinvent the results in that paper in various ways. And so that is the last thing that I want to mention. Here is that Rao Varadarajan paper. So that appeared in Sankha. So they were considering these anthropometric measurements, and as I said, the number of variables were very large. Okay. So at times they run into this difficulty that this sigma matrix, for which you have to compute the inverse, it was not invertible because you are computing it from the data. Okay. So they were at a loss at that time. So today we know a lot of these regularization techniques and many other techniques to deal with the lack of invertibility in the dispersion, but those were not known to C.R. Rao and his co-workers at that time. Okay. But they were concentrating on some theoretical problems with like Varadarajan, and they considered this problem of discrimination problem of Gaussian measures in infinite dimensional spaces. Okay. See, one way to deal with this very high dimensional data is to think about high dimensional data as something like an object which is something like a set of points which are embedded in an infinite dimensional space. Okay. So you pretend that it's really coming from an infinite dimensional space, but you are looking at something like a finite dimensional projection of it. Like when you look at the ECG curve of an individual, you take the measurements at definite time points. But suppose you are able to measure it continuously over time, then it will be an infinite dimensional object. Okay. But you actually measure it at only a few time points, so it's really a finite dimensional thing, but it's a very high dimensional thing. Okay. So when Varadarajan and C.R. Rao were working on this problem, so that is the slide that I had there a few minutes ago. So these are two very interesting discoveries they made. So two Gaussian probabilities with positive definite covariance in finite dimensional spaces are always mutually absolutely continuous, meaning that it's like one distribution is absolutely continuous with respect to the other and vice versa. So if you want, you can always form the likelihood ratio, and that will give you the Bayes risk optimal classifier. Okay. Unfortunately or fortunately, this does not happen to be true in infinite dimensional spaces. In infinite dimensional spaces, you can have two Gaussian probabilities with positive definite covariance operators, but they may be orthogonal. It's a beautiful result. And they also gave when they are mutually absolutely continuous, the sufficient condition for that. Okay. So two Gaussian probability with common positive definite covariance operator are mutually absolutely continuous if and only if the difference between their means lies in the range space of the square root of the covariance operator. Remember, what is the Mahalanobis distance? It is so let me go back. Now think of all these things as infinite dimensional objects. So sigma is a covariance operator now. Now if it is a covariance operator in an infinite dimensional space, just being positive definite does not mean it is invertible, because it may not be onto. That's the basic difference between an infinite dimensional vector space and a finite dimensional vector space. 1, 1 does not imply onto. You have learned that in your linear algebra, right? In infinite dimensional space, it's not true. So if it is not onto, if I just give you mu1 minus mu2, it may not be in the range space of sigma inverse. So I may not be able to compute Mahalanobis distance. And when you are not able to compute Mahalanobis distance, Varadarajan Rao paper is telling that then the two probability measures are going to be orthogonal. So they are well separated. You don't have to worry about classifying them. They are sitting on two disjoint sets. So it's a beautiful result. And this is something that he did in 1963. Yes, 1963. So this is the first and most fundamental work on classification in infinite dimensional spaces. This sort of is like the foundational result where classification in infinite dimensional spaces begin. Okay. Those of us who have spent an enormous amount of time in our research career along with our PhD students developing classification for high dimensional or infinite dimensional data, this is sort of like the foundation.
Culmination.
Yes, this is the culmination point, that in infinite dimension things are very different. There may be either mutual absolute continuity when you have the same base classifier, the Fisher's linear discriminant function. And if it's not, then the problem is trivial. Now, is this true for non-Gaussian distribution? Is it true only in Hilbert space, or it is true in more complex spaces like Banach spaces? Kollanpur worked on this problem when you have probability measures in Banach spaces, and he gave more interesting and more technically involved characterization of these things. So I think I will leave it here. If people are interested in doing research in this area, this RAO Varadarajan paper is a must reading for everybody. Okay? So you should read this paper before you take up your research in statistical inference in infinite dimensional spaces. Okay. Thank you all.